Hey, Bivile. These are the answers to the water potential equations. So we'll give you a quick rundown on these, talk a little bit about them just to make sure that you guys are all set. And after that, we should be good to go. So question one gave you this scenario. A cell is in equilibrium with its surrounding at 30 degrees Celsius. Okay. The molarity of the surrounding sucrose solution is 0.5 molar. So first they want you to calculate the solute potential. Okay. So solute potential is going to be your negative I CRT equation. Negative I, right? So sucrose has an ionization constant of 1. C is your concentration, right, which they gave us here, 0.5 molar. R is our 0.0831 pressure constant. And then our temperature is 273 plus 30 degrees. So that's 303 degrees Celsius. Okay. That gives us a negative 12.59 solute potential. Okay, now the water potential of the surrounding solution. Water potential is your solute potential plus your pressure potential. Now, since it's in a solution, it's unless there's pressure given to it, we always assume it is an open system, so there's no pressure. So therefore, the water potential and the solute potential are the same. Now, the next question, a little tricky. They asked what was the water potential of the cytoplasm of the cell. Now, the cell's already in equilibrium. So because the cell's in equilibrium, we know that the cell has to have the same water potential as the surrounding solution. Okay. Okay. Number two, you have a water potential of a cell and it's negative 0.24 kilopascals. So if you add pressure to that of 0.46 kilopascals, you want to know what is the solute potential of that cell. So you measure the water potential, okay, and it comes out to negative 0.24. Okay, so the pressure potential, you already have pressure being added to it, is 0.46. They want to know what's the actual solute potential. So X would have to be 0.70, okay, because it's your solute potential, which is right here. 0.70 plus 0.46 gives you negative 0.24, okay? If there was no pressure, your solute potential would be your water potential, okay? All right, number three, you have a cell with a solute potential of negative 0.67 and its pressure is 0.43. So you always add the pressure, okay, which means now your potential is going to decrease to negative 0.24, okay, or rather increase. Okay, so it starts off as a really low negative 0.67. When you add 0.43 to it, it becomes negative 0.24, okay? All right, moving on to number four, you have a hypertonic environment. The water potential of a hypertonic environment is always going to be low. It's low because hypertonic is more concentrated. So something that is more concentrated means it has a higher molarity, which means its water potential is lower. Okay, water potential and molarity are inversely related. The more concentrated you get, the higher the concentration, the higher the molarity, the lower the potential, the more negative it gets. Okay. All right, moving on to number five. Okay, so you have a pressure potential. It's 3 bars. You're adding that to negative 4.5. So when you take a negative and add a positive to it, you still have a negative number here because negative 4.5 is a very negative number. Okay, and so we're at minus 1.5 now. That's our water potential. Okay. Now, if we take a cell from question 5, right? So here's our cell, okay, with this negative 1.5, and now we add it to a beaker with a solute potential of negative 4. Which direction will the water flow? It's going to go out of the cell. Why does it go out? Because water always goes from the higher potential to a lower potential. Negative 1.5 is a larger number compared to negative 4. Okay? So the water is going to go from the higher number to the lower number. It always flows down the gradient. Okay? It goes out of the cell. Okay, now you take that same cell. Now you put it in a beaker of sugar water that's negative 0.15 megapascals. Now we know that 1 megapascal is 10 bars. So if you do your math, you know that that's equal to 1.5. Okay, multiply by 10, move your decimal. So that beaker is 1.5, the cell is 1.5. There's no net flow of water, okay, because they're in equilibrium with each other. Okay. All right, moving on to number 8. Okay, so root tissue is measured to be negative 3.3 bars. So we put that in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker. So what we need to do is calculate right here, we calculate the water potential, which is the solute potential of that particular solution. Okay, it's negative 2.43. The root is negative 3.3. So the root has a lower potential. It's more negative. So water is going to go from negative 2.43, which is a higher number, to the lower number, negative 3.3. Water is going to flow into the root. Okay, it always goes from the higher to the lower potential. Now, if we go to number 9, we have the same scenario here. Okay, we take that same solution, and now we say, okay, instead of sugar, now it's 0.1 molar sodium chloride. So now what would be the water potential of that solution? So now all we're doing is we're changing the ionization constant. It goes to negative 2. Why does it go to negative 2? Because sodium chloride dissociates into 2 particles. So its ionization is 2. So that gives us a number of negative 9.74. The root tissue is negative 3.3. So now the water is going to flow from the root to the solution because now the solution has a lower potential. Okay, it's more negative. So it goes from the less negative to the more negative number. Okay, 3.3 is a larger number compared to negative 9.74. Water is going to flow down the gradient. Okay, number 10. You have a plant cell. It's negative 7.5 bars. You keep a constant volume when immersed in an open beaker. Okay, and you know that that open beaker's got a potential of negative 4. So what is that cell's pressure potential? So if it's in equilibrium and its volume is the same, that means that although it has a solute potential of negative 7.5 bars, you put it in a beaker that's negative 4. That means that the plant has to have a negative 4 water potential. So how do you get that? You have to add pressure. Okay, so 3.5 would be the pressure you add to that. Okay, and that gets you a negative 4. Okay. All right, number 11, last one. This was tricky. 20 degrees Celsius, you have a cell with a pressure potential of 3 bars, and that's in equilibrium with the surrounding 0.4 molar sucrose solution. They want to know what is the molar concentration of sucrose in the cell. So first, we need to figure out what is our actual water potential. Okay, we know the pressure is 3, but what's the actual water potential? So first you have to calculate solute potential of the beaker. Okay, and then we can figure out what's going on with our cell. So the beaker is 0.4 molar. Okay, and so when we calculate that, we get negative 9.73. Okay, now with the pressure added, it's negative 9.73. Okay, that's our solution. So we want to know what's the molar concentration of the sucrose in the cell. Okay, so without pressure, we know it's negative 12.73. Okay, so our cell with pressure added to it actually has a more concentrated solution. Okay, so now we have to figure out, okay, if our cell is normally negative 12.73 without pressure added, okay, remember the pressure that's added raises the potential. Okay, so without pressure, we lower it. So this is what our solution is. So that's inside of our cell. Okay, we're going to just go with the assumption negative 1 and everything else is constant. So we have to solve for x. So if you multiply these out, divide by 12.73, x is equal to 0.52. I'll give you some wiggle room around 0.5 molar. Okay, and if you plug that in, you'll get negative 12.73. And that's what our molar concentration of the cell can be determined from. Okay, and we figured that out by determining what the actual osmotic potential of the cell was without the pressure. And that's it. If you're still not sure about some of these, please reach out to us. Either email, remind. We can definitely do an explanation. Okay, but that's it for water potential. At most, you might get a question on the AP test on this. Who knows? There's so many different things they can ask, but we want to make sure that we covered all the bases with you guys. Okay, so that's it. Be well, and we'll see you soon.